First of all, I wish to thank the organizers. It's a great pleasure to be here, and I'm very happy to have the possibility to give a talk in such a beautiful meeting. So I would like to start giving a brief summary of the so-called Cheeger-Goresky-MacPherson conjecture and MacPherson's conjecture. So the Cheeger-Goresky-MacPherson's conjecture has been stated in 1982. The setting is a projective variety within a complex projective space. And on the regular part, we consider the Fubini-Study metric. So the conjecture says that, the maximal and the minimal extension of the Ram differential are the same. Sometimes this property is called L2 Stokes theorem. The second requirement is that the L2 cohomology is isomorphic to the intersection cohomology. And finally, we can use the L2 Dolbeault cohomology to get a decomposition of the intersection cohomology, getting what is called a pure Hodge structure on the intersection cohomology group. I don't have enough time to recall the various contributions or result in this direction, but let me say that this conjecture is still largely open. The second conjecture that I would like to recall is the so-called Pardon conjecture. This has been stated in 1983. So we have again a projective variety, and we consider a resolution, V tilde. And on the regular part of our projective variety, we consider again the Fubini-Study metric. So the conjecture says that the Euler characteristic of the sheaf of holomorphic function of the resolution is isomorphic to the alternate sum of the dimension of the L2 Dolbeault cohomology of the regular part of V. Since we are within an incomplete Kähler setting, part of this conjecture is to understand what is the right closed extension to take into account. This conjecture has been solved in 1991 by Pardon and Stern. Actually, they prove a stronger result. They show that the right closed extension to consider is the minimal one, and we have an isomorphism for every single L2 Dolbeault cohomology group, not just for the alternate sum. Okay, so these two conjectures has been the source of many important related problems. For instance, extension of self-adjoint extension of the Hodge Laplacian and of the Hodge-Kodaira Laplacian with discrete spectrum. This is basically completely open. Estimate for the growth of the eigenvalue. Trace-Cass property, and index formulas, but many others. This is just a very brief list. The goal of this talk is to give a brief summary concerning a recent result that I proved about these two questions. So let me introduce the setting. We have a complex Hermitian space. So this means that we have a complex space, and the regular part carries an Hermitian metric, which is locally given by an embedding. For instance, a natural example is given by you take a complex Hermitian manifold, you take an analytic subvariety, and then you take the restriction of the ambient metric space over the regular part. As a particular case of this class of examples, we have a projective variety with the Fubini-Study metric. Okay, from now on, we restrict ourselves to the case of compact and irreducible Hermitian complex space. And in general, with M, I will mean the complex dimension. Okay, so we are interested in this operator. We consider the regular part of our complex Hermitian space. We take the canonical bundle of the regular part, and then we take the Dolbeault operator acting on the canonical canonical bundle of the regular part. And let's say the domain, the starting domain, is the smooth section with compact support. With the capital D bar, I will mean any closed extension of the Dolbeault operator. And capital D bar will be the Hilbert space adjoint. So for example, the operator capital D bar can be the maximal extension of the Dolbeault operator or the minimal extension of the Dolbeault operator, which in general are the most common extension to take into account. Now, I'm going to introduce this operator. I take the composition of the capital D star with capital D with the natural domain, so the section that lies in the domain of capital D, such that the image lies in the domain of capital D star. This guy is a self-adjoint extension of the Kodaira Laplacian acting on the section of the canonical bundle of the regular part. Okay, now I gave the setting and I can state the result. So this operator has discrete spectrum. Whatever it is, this closed extension, you always get an operator with the discrete spectrum. If we label lambda k the eigenvalues of this discrete operator, then we have this asymptotic inequality. The lim-inf of lambda k times k at minus 1 over m is positive. So we can reformulate this inequality saying that there is a positive constant c and a positive integer n such that lambda k is bigger or equal than c times k at 1 over m, where when k is greater or equal than n. Okay, let me stress about a couple of properties. The no assumption on the singular subset. There were no assumption on the dimension of X. And as I said, the result also for any self-adjoint extension of the Laplacian that you get fixing a closed extension of the Dolbeault operator and taking the composition with the Hilbert space adjoint. So in particular, it's true for this extension, the maximal extension of the Dolbeault, composed with the minimal extension of the formal adjoint. And it's true for this other self-adjoint extension, the minimal one of the Dolbeault, composed with the maximal one of the formal adjoint. Let me remark that this is the Friedrich extension of the Laplacian acting on the canonical bundle. Okay, now I would like to give you a brief sketch of the proof. So the first goal is to show that this guy has a discrete spectrum. This is true if and only if the inclusion is a compact operator. So the first property is that we have a continuous inclusion of this domain into this domain, where each domain is endowed with the natural with the corresponding graph norm. This is a pure functional analytic fact. Okay, now for us having this continuous inclusion is enough to prove that this inclusion, the domain of the capital D bar, is compact. To prove this goal, we need to introduce a resolution of X. So we have a compact complex manifold. We have a nullomorphic map, which is surjective, and such that there is an open and dense subset on X, such that the restriction of pi over A is a bilomorphism. And the complementary part is the support of a normal crossing divisor. With rho, I will label the pullback of H. So what I'm going to get is a positive semi-definite Hermitian product on M, which is strictly positive on A. Sorry, this is a mistake. On A, not on M. And with this little bit abuse of notation, I will mean the operator on this new setting, which is unitary equivalent to the former operator through the pullback given by pi. So, we are going to move from the singular guy to the resolution. Finally, over M, the resolution, we consider an arbitrary Hermitian metric. And this guy is the unique closed extension of the Dolbeault operator acting on the canonical bundle. Now, I can say that, in this case, in this context, we have only one closed extension because, now this is compact and the metric is not degenerate. So, okay. So the statement, that is the compact embedding of the domain of this guy, is a consequence of the following properties. First, we have an equality of Hilbert spaces. This is essentially a consequence of a linear algebra, a property of Hermitian metric, let's say. Almost a purely, algebraic result. You compute the fiber-wise metric, you compute the new fiber-wise metric, you compute the new volume form, you multiply, and then you see that is again the original one. So we have this kind of stability of Hilbert space. We have a continuous inclusion of domains. The one on the left is the domain of this guy, while the domain on the right-hand side is the domain of the Dolbeau operator acting on the wall resolution. And of course, every domain is endowed with the corresponding graph norm. And finally, we have a compact inclusion. So, summarizing, this is the domain of the original self-adjoint extension of the Hodge-Kodaira Laplacian. We have this continuous inclusion. We have another continuous inclusion. This is a compact inclusion, but the Hilbert space is stable. So actually, this is the original Hilbert space. Take the composition, I have a compact inclusion of the domain of the Laplacian into the Hilbert space. Okay, let me add just a couple of comments. As I said, this is, let's say, a bit more than an exercise of linear algebra. You calculate the fiber-wise metric, the new volume form, and you can check that nothing is changed. The fact that this is a compact inclusion is a standard fact from elliptic theory on compact manifold, because this guy is an elliptic complex. So in the list of ingredients that I gave you before, the subtlest point is to show that we have a continuous inclusion of this domain into this domain. This is a consequence of the following properties. I need to use again the fact that the Hilbert space is stable under changing of Hermitian metric. I need to use this new property that, if we change B degree and we go from M0 to M1, now we have a continuous inclusion of Hilbert spaces. I need to use that, let me recall that A is the open subset of M, which is bilomorphic to the regular part of X. So I need to use that this guy is parabolic. Parabolic means that there is a sequence of Lipschitz function, non-negative, bounded above by 1, that point-wise goes to 1, and whose energy goes to 0. And finally, the final property is that this operator, the Hodge-Dolbeau operator, is essentially self-adjoint on this space. So A is as I said, is the open and dense subset bilomorphic to the regular part. And here I'm considering the restriction of the metric on M over A. Okay, so putting together all this property, you can get this continuous inclusion, and then this is the missing point in the chain of inclusion that I showed you before. And finally, I can conclude that that operator is an operator with a discrete spectrum. The second important property is the asymptotic inequality. So I need to use again the fact that I have a continuous inclusion of domain. I need to use again the fact that I have a continuous inclusion of Hilbert space. And finally, I use the min-max principle. Because, using the min-max principle, you can characterize the eigenvalues in a variational way using the quadratic form associated operator. So we have an inclusion of the domain of one operator into the other one. And since we have also an inclusion of Hilbert space, we can provide a satisfactory comparison. Okay, now let me give you an application of this result in the more restricted set of complex projective surfaces. So, we have a complex projective space, and we fix projective surfaces. And of course, on the regular part, we consider the metric, the Kähler metric induced by the Fubini-Study metric. Now, I'm going to consider the Hodge-Kodaira Laplacian. And again, let's say I'm going to consider the B degree 2Q. So let's say those associated to the complex starting from the canonical bundle. Now let me introduce this self-adjoint extension, which in general is called the absolute extension, and is defined taking the maximal extension of the Dolbeau operator with the composition of the minimal extension of its formal adjoint. And the domain is the natural one. And we take forms that lies in the intersection of this domain with this other domain, and such that the image of omega is contained in the domain of the subsequent operator. So this is the Laplacian coming from the Hilbert complex given by the maximal extension of the Dolbeau complex in B degree 2Q. Okay, so what I would like to show is that, I mean, combining the result that I show you right now with a result proved by Lee and Tian in 1995 and another result proved by Pardon and Stern in 1991, we have the following result. So I consider again this, a projective surface within a complex projective space, Fubini-Study metric over the regular part. And I consider again this self-adjoint operator. So those guys have a discrete spectrum for every Q. So in this case, I have a full description of all the Laplacian associated to the complex. Moreover, I mean, if I consider the eigenvalues, then I have again the same asymptotic estimate. Now let me give you a very brief sketch of the proof. So the case in B degree 2,0 is an immediate consequence of the theorem I show you right now. The case 2 is a consequence of the theorem of Lee and Tian. Actually, they prove several stuff in that paper, but in particular, they prove this result of discreteness with an estimate for the spectrum, in the scalar case. Now it's just enough to take the Hodge star operator, and then you take the same result in this B degree. So what is missing is the middle degree, 2, 1. Now, I mean, in this setting, we need to use the result of Pardon-Stern, and so we know that the cohomology of the whole complex is finite dimensional. So in particular, this means that this operator is a Fredholm operator. The null space is finite dimensional, and the image is closed. Since we want to show that this operator is discrete, we would like to show again that the inclusion of the domain is compact. But we know that the image is closed and the null space is finite dimensional, so it's enough to show that this inclusion is compact. Because what is missing is the kernel, but it's finite dimensional. Okay, that the previous inclusion as a compact operator is a consequence of this following general statement. I mean, it holds in for a short complex of Hilbert spaces. So I have 3 Hilbert spaces, H1, H2, and H3, and 2 operators, T1 and T2. T1 is acting from H1 to H2, and analogously, T2 is acting from H2 to H3, and both of them are densely unbounded, densely defined, and closed. Moreover, we want that, I mean, the image of T1 is contained in the domain of T2, the image of Tk is closed, and the composition is identically 0. Now, I mean, I consider the associated Laplacian, which is an operator acting on H2. And what I have is that these following 2 properties are equivalent. So the first one is a pair of compact inclusion. This is on H1 and this is on H3. On H1, I'm taking the domain of T1 composed with T1 star intersected with its image, which is closed, and endowed with the corresponding graph norm. And I'm doing the same stuff on H3. And it turns out to be that this pair of compact inclusion are equivalent to the fact that this inclusion in H2 is a compact inclusion. So since, I mean, we have a complex made of 3 pieces, and we already know the result in B degree 2,0 and 2,2. Actually, we know more. We know that the Laplacian are discrete. We can conclude that the corresponding inclusion is compact. And since we already know that the null space is finite dimensional, the operator is discrete. Okay, so finally, I'm going to close the exposition with a brief application. So the previous theorem on surfaces, we can use it to restore the Mckean-Singer formula for complex projective surfaces. So the quality on the left-hand side is a consequence of the theorem that I showed you before, and is due to Pardon and Stern. This is the quality on the right-hand side is a consequence of the theorem that I show right now. Because using that estimate of the growth of the eigenvalue, we can prove that the it operator associated to the Laplacian are trace classes. And so this means that the Euler characteristic of the sheaf of holomorphic function on the resolution is the alternate sum of the trace of the it operator of the absolute extension of the Laplacian on the regular part. And the dual result is that this is the sheaf of holomorphic 2-0 form. The dual result is that the Euler characteristic of the sheaf of holomorphic function on the resolution, again, this equality is due to Pardon-Stern, is the alternate sum of the trace of the it operator associated to the relative extension on the regular part of the variety. Okay, this is just a brief description of the ingredients involved in the formulas. Okay, so this was the last piece of the presentation. Thank you very much.